So today is a fun day. We're just going to talk about stuff that's interesting and cool and fascinating. And, why might you want to take a class like this to learn differential geometry? Sort of a continuation of what we did last time, a little bit. And then next week we'll actually get into the, chapter 1, right? And we'll start doing curves and surfaces in R3. And you guys know all the information is on the website. So you can not only start on the homework due this week, but then next week, the week after that, get as far ahead as you like. I encourage it. We're doing something new for the first time, and I would like your feedback. I actually have the videos from 2018 posted on the course webpage, and I have it as homework for you guys to watch the videos. Okay? Now, I will have no way of knowing if you actually watch the videos or not. And frankly, I'm not even positive if you should or you shouldn't. I want to let you guys figure this out, okay? So I recommend it if you could watch those videos before we cover the material, right? And stay ahead, that might be a good thing, right? You also can reference those videos after I present the material in class. And if you didn't understand something or you thought you did, but wait a second, how did that go? So you told me if it ends up being useful or not. I figure I had the videos, I might as well let you guys reference them. The video quality is 2018. It's circa 2018. It's a little bit embarrassing, but I think you can hear the words and you can see the equations, and so if you find it useful, let me know. So this course is about curvature, really. If I had to pick one word, like what is curvature? And really, another way to think of it is there's single variable calculus, then there's multivariable calculus, and then there's multivariable calculus on curved spaces, and we call it differential geometry. Right? So it really is in that progression. And as I said last time, this differential geometry apparently, to say it provocatively, right, God apparently is a differential geometry. Right? I mean, the universe is described by differential geometry, just undeniable. By the way, a lot of other areas of mathematics as well. It's really kind of interesting how if the math that we find important and fundamental tends to show up in physics, and that's caused some people to speculate maybe physics and math are the same thing. I've heard people say that. I'm like, well, what do you mean? But they can't really explain. But there seems to be a deep connection between math and physics. And so last time we talked about how putting a minus sign in the rule of Pythagoras gives you special relativity. And so, sort of the simplest example of a space-time then would be just that. And so special relativity is general relativity in the simplest case. So I drew the light cone last time, right? Pretty sure? And if you want to take a dot product of a vector, like this vector here, and it has components vt, vx, vy, and vz, then the only difference is that v dot w is equal to, has a minus sign in the dot product. But really, this is the fundamental difference. I didn't draw W, but you get the idea. And by the way, there's a notation. And by the way, and so that means, for example, V dot V, right, would be minus the time component squared plus the X component squared plus the Y component squared plus the Z component squared. And as we talked last time, V dot V could be 0, negative, or positive. If it's negative, we call it a time-like vector. If it's positive, we call it a space-like vector. If it's in between 0, we call it a null vector. And in particular, this is still equal to the length of V squared. But it has to be up to a sign, obviously, right, because that could be negative, right? So it's up to a sign. Then we'll interpret that as the length of V squared. And what the sign of V dot V is, that's how we decide what kind of vector it is. Did I do the twin paradox last time, too? I think so, right? Yeah. And so you get the twin paradox from this. And guess what? The twin paradox has been experimentally verified. This isn't just, oh, by the way, here's some crazy thing that this theory predicts. They have put super accurate clocks, atomic clocks on very fast aircraft. They'll take one, take two, they'll sync them up, right? They say exactly the same time to a billionth of a second. Put one on a super fast aircraft, fly as fast as they can, land it, put them next to each other, twin paradox. Just a little bit, right? Can be measured. And by the way, it can be measured. Now, the problem is we can't get going close to the speed of light. That's the engineering problem. Now, there are subatomic particles that come into the atmosphere that are going pretty close to the speed of light, and they have radioactive decay, and they can measure, the radioactive decay as sort of a clock, and guess what? Check mark, right? It works, right? So this special relativity thing appears to be the way the universe works to some approximation, And so what does it replace? It replaces the Newtonian way of looking at it. Right? This unifies space and time, right? Which is deep. I hope we can agree on that, right? Like, whoa, what a deep idea, right? Space and time are two sides of the same coin. And so are we saying that space and time are the same thing? No. I think it's, by the way, if I say something is too crazy, you can raise your hand and call BS on me, okay? I encourage you to do it, all right? If I tell you 3 equals 2 and you're like, see, Einstein, you should question that, okay? So at some point when I say if I were to say space and time are the same thing, you should be like, no, it's not, obviously, right? But space and time can be measured in the same units. Turns out 1 year equals 1 light year. Okay, that's the conversion factor. The analogy I like to make is milk and soda pop. Are milk and soda pop the same thing? No. No. If someone ever tells you that milk and soda pop are the same thing, you should say, no, they're not. However, they can be measured in the same units, either liters or gallons. Now, if you go to the grocery store, you'll see that milk comes in gallon jugs and soda pop comes in 2-liter jugs. Right now, I don't know why they do that, but they do, right? And so imagine a world where no one ever realized you could convert between liters and gallons, right? And they were always selling soda pop in the 2-liter jugs, and they were always selling milk in the gallon jugs. And then this guy named Einstein comes along, and he says, did you know that approximately 4 liters equals 1 gallon? And then someone's like, what? He's like, yeah, you can convert between liters and gallons. Like, that would be like converting between distance and time. And then people are like, but soda pop and milk aren't the same thing. And then Einstein's like, yeah, I know that soda pop and milk are not the same thing, but they're measured in the same units. You can convert between the 2 units. There's a conversion factor. And that conversion factor is the speed of light. Conversion factor for, what is the speed of light? We use the letter C for it, and it's around 300,000 kilometers per second, which means 300,000 kilometers equals 1 second. Another way to say it is 1 light year is equal to 1 year, right? That's speed of light is the conversion factor between space distances and time. So, I like the milk soda pop analogy. And, maybe, hopefully this doesn't seem quite so radical. I mean, does it seem plausible to you guys? Now, it's a little bit shocking. I mean, it didn't have to be this way. Like, this is not how Newton looked at it, right? Newton said there was space, x, y, and z, right? And you guys learned multivariable calculus. It was always x, y, and z. No one ever said, you could have a function of t. Maybe you could have a curve in x, y, z space, right? You could have a function of t. But no one ever, when you do a rotation, you rotate in the xy plane. You might rotate in the yz plane, right? You wouldn't ever rotate in the tx plane, right? That's crazy. Like, what are you talking about, right? Newtonian physics doesn't have any mixing of space and time, right? There's a universal time coordinate. And by the way, our brains are set up to perceive a universal time coordinate, right? We're like, hey, what time is it? We all have watches, and we all agree on what time it is. And so we think we're just intuitively set up to believe there's a universal time coordinate. Okay, so that is, in fact, a fiction. There is not a universal time coordinate. There is to a high degree of approximation, right? To a high degree of approximation, right? And that's the difference. So you might say, hey, I have to call BS on that. There is a universal time coordinate. How come we all know what time it is, right? Well, it's because we all like to go for jogs, but none of us jog near the speed of light, right? We all have like a fast car, or, not really, right? But But no one's driving speed of light. No one's getting in an airplane going the speed of light. And if we did, by the way, then there would be no universal time coordinate. I actually think that would be an awesome movie. I would go to the theater to see that movie. If they could make a movie that shows what life would be like if the speed of light was like 10 miles an hour. That would be fascinating. Because that would mean that time travel would be an everyday reality. Okay? Because the twin paradox would be all over the place. You go for a jog, it seems like 30 minutes to you, but now you just jog 5 hours into the future. Okay? Depending if you can run fast. If you could average close to 10 miles per hour. Now, by the way, the 10 miles an hour would be the cosmic speed limit. So as you start jogging, right, like you might say, oh yeah, I can jog 10 miles an hour, right? I'm a pretty good runner, right? No, you can't. Not if the speed of light is 10 miles per hour, right? Then the point is you notice, okay, you get up to 5 miles per hour, and it's like, okay, and then and it's really a lot harder to get to 6 miles an hour, and then even harder to get up to 7 miles per hour, right? And and that's where the relativity comes in, because if you're jogging 7 miles per hour, the point is that according to relativity, there's a certain point of view that you're at rest and the Earth is moving 7 miles per hour that way, right? And so in special relativity, all inertial means non-accelerating, all non-accelerating, inertial reference frames are equally valid. That's the relativity, right? And in general relativity, it's even more general. It gets more complicated. A lot of people kind of mix these things confused. In special relativity, you can only use non-accelerating frames of reference are equally valid. The laws of physics should be the same in all non-accelerating frames of reference. In general relativity, as we'll describe, there's no definition of what a non-accelerating frame of reference is anymore. We have to get into the language of differential geometry, which we'll learn about in this class. And so it gets quite a bit more complicated. Okay, even by the end of this class, you still really won't fully have general relativity exactly. You'll be getting very close, though. And so in general relativity, really you can use any quote-unquote coordinates that you want, right? Any coordinates. And then the equations are because it's so general, right? The equations get quite complicated. But they're also very natural. And there's only a few ways it could have been. And I'll explain that in just a second. So let me just pause there before we get into general relativity now. Does anyone have a question they have about special relativity? Yes?
Why in the formula for the magnitude of v squared, why is it plus or minus in front?
Oh, that's because, I'll answer your question, but I'll answer another question first, which is a precursor, which is, why is that minus sign there, first of all, right? And that's an axiom. Let me just emphasize that, right? The special relativity, sort of this is what is the definition of special relativity. You put a minus sign in the rule of Pythagoras, okay? That's a definition or an axiom. There's no proving that. It's the way we currently perceive it. And then, well, why do you have to put a plus or minus there? Well, this could be negative, right? I mean, unlike that, if we're all positive, then this would have to be greater than or equal to 0. Because of the minus sign, it could be negative, right? So let's say I wanted to compute the length of 5, 0, 0, 0, right? Then I would get this to be minus 25. And then so if I didn't have the plus or minus there, then I guess the length of v would be the square root of minus 25. So what you could call it 5i or minus 5i, right? And we could have done that. You could just say some lengths are pure imaginary and some are real. But we're just like, you know what? Instead of doing that, you could have, right? Let's just say, because that seems a little weird to call length imaginary, right? So we'll just go ahead and say, look, it could be positive, it could be negative. Whether it's positive or negative defines whether it's space-like or time-like, right? If it's negative, we call it time-like. If it's positive, we call it space-like. Because the up and down vectors, whether they're pointing up or down, they're going to tend to have they will have the negative answers. You'll be inside the light cone. And if you're outside the light cone, pointing in spatial directions more than time directions, then you'll get a positive value there. Does that answer your question?
It does. Thanks.
Great question. Yes.
In relativity, is there any meaning sort of ascribed to the norm of a vector or taking the dot product of the vector with itself? Because it would seem to imply that there's some sort of absolute zero in time or in space, right?
Yeah, this has meaning for sure, right? And in fact, remember when we were talking about the twin paradox, right? And I'll draw a more realistic image here where you have a smooth curve, right? Where you have two world lines, one for observer A and one for observer B, right? Then the amount of time they experience is the length of their world line, right? So the interesting thing then is the geometric thing, length, right, is equal to time experience, as I said last time. But how do you compute the length of a curve? Well, you break it up into a bunch of smaller curves, right? And each of these is somewhat linear, and so you can take this vector here and say, hey, what's the length of that little vector, right? And that's where this formula comes into play, right? So ultimately, this formula is what you use to sort of, to add up the length of a curve, right? So yeah, this is telling you if I go from this point in the space-time to the vectors in the special relativity model, how much time is experienced by someone going along that straight line path. So that's a physical interpretation. Right. By the way, more generally, there's something, why does length equal time experienced? Okay, let me throw that question out to you real quick. But before I tell you the answer, right? Let me tell you what's going on here, which is, imagine I wasn't lecturing on general relativity and special relativity, but it was hundreds of years earlier, and I was trying to explain Newtonian physics to you. It's a good subject, right? You all enjoyed it. Guess what? It's wrong. It's a nice approximation. It's appropriate for high school, maybe freshman year, college, right? That kind of thing, right? Yeah, learn it first, right? But let's not forget that it's wrong. Okay? There are experiments you can do in physics that contradict Newtonian physics, right? Still, a great admiration for it as a breakthrough in science and so forth, right? No disrespect to Newton, one of the greatest thinkers of all time. Some people say the greatest, right? But it's wrong. Guess what? No disrespect to Einstein. But general relativity is wrong too. It's no different. Okay, this is not the last theory. This is what we think is a good idea. We're like, oh, look what we figured out. Right? But let's keep it in perspective here. The really interesting question is, okay, be skeptical because it is wrong. I guarantee you that. Or at minimum, it's incomplete. Right? Now, general relativity is amazing in what it can do, in the same way that Newtonian physics was amazing at the time, right? But how is it incomplete? Well, we know there's this other theory called quantum physics, and which uses quantum field theory and the standard model of particle physics. It's actually an amazing theory too, pretty intricate. It describes every laboratory experiment you can do with particles. Really amazing. I actually am not an expert at that. I was a physics major as an undergrad, but I did not do my PhD in physics. I'm an expert at general relativity, so that's on that side of physics, but I'm not an expert on quantum physics. And guess what? I know a lot of people who are experts at quantum physics, and they tend not to be expert at general relativity. They know something, just sort of like I know something, right? And the reality is no one knows how to combine these theories. Not a single person on the planet understands. Every person who thinks about it knows these theories should be two aspects of a greater theory. But not a single person knows how to combine the theories into that one theory of everything. That's where we are. And so when you look at general relativity, and I explain it to you, just realize that this is just the best people could figure out so far. Right? And so the big idea here, why is length equal time experience? Well, the bigger idea is that math equals physics, or that in this case, geometry equals physics. Right? We're like, okay, we have this thing called length. Oh, okay, that's a geometric thing, right? Okay, that seems important. Okay, I wonder how what kind of experiment could we use to measure, like, oh, maybe the length of your world line is how much time you experience, and then you do the measurement. Oh, hey, that worked. Okay, well, let's make this a rule. We'll define special and general relativity to say that the time that you experience is the length of your world line. And so it agrees with the experiment, but it's also like an educated guess. You might conjecture it, you do an experiment, you see what works, right? Oh, okay, this is what seems like it works. Okay. Other questions? And so that takes us to general relativity. And so let me tell you how, it's on the most basic level, the way I think of it is, well, there was a problem that Einstein had, and we should enjoy Einstein's problem, right? Einstein came with special relativity first. And by the way, there's a cultural thing here that's really fascinating, which is Einstein came with special relativity, which I think we have to agree is genius, right? You put a Einstein the rule of Pythagoras, like who said you could do that? Well, by the way, he didn't do it. He thought of it a completely different way in his genius, whatever, however he did that, right? And then his math professor said, oh, hey, Albert, I see what you're doing. You put a minus sign in the rule of Pythagoras, right? Okay, but nevertheless, Einstein conceived of special relativity. And this is because of the Michelson-Morley experiment, as I mentioned before, right? That the speed of light seems to be the same no matter how fast you're moving. And so he then was able to define special relativity and says, this solves the problem. And if you want to understand more, watch my videos. My videos explain that quite well. Go up to the one where we talks about it's in the first 7 or 8. And you can see why putting a minus sign in the rule of Pythagoras predicts a constant speed, a uniform speed of light. The speed of light will be the same in all reference frames. That's obvious from what I've said so far, but it's true. And watch my videos if you want to get to the bottom of that. It's really super cool. I think it's a video called "The Universality of the Speed of Light." Right, it's a cool video. No, I mean, look, I don't get the credit. Einstein. If you want to understand what Einstein's first great idea was that put Einstein on the map, watch my video, "The Universality of the Speed of Light." Right, and any videos that come before it if you need to, but just you can skip to that one, and you'll say, nice. That's what's called a paradigm shifting idea. Like someone just broke the assumptions, right? I mean, you got to have some nerve to do that. Newton said for ages, right? Like you got X, Y, and Z, you got T, they're completely separate, right? And all of a sudden, this person your age says no to Newton. No, it doesn't work that way. Let's try something else. He has the gall to question the conventional wisdom, right? Now, I like to think Newton would not be insulted at all. Newton would be impressed, right? Because it probably wasn't Newton going around saying, you must think like I do. Smart people, geniuses, they don't do that, right? They're the creative types. They're questioning everything, right? So question everything. Einstein was a question everything person. Oh my goodness, wow. And then he figures it out, and guess what? Nobody believes him. I mean, it's like the resistance. Like, a few people got it, right? But of course, most people are like, hey, who do you think you are? Right? But it worked, and so the people who were the top people of his day got it quickly and realized, okay, this guy's onto something. And so he became recognized by the top experts. But there's still this underlying level of skepticism in the background by sort of most people. And in particular, there was a problem with special relativity, which is it wasn't consistent with our notion of gravity. And of course, Newton had gravity. And so here's this upstart guy saying, I've got this better idea, this unifies space and time. But even Einstein had to admit his theory did not incorporate gravity. Doesn't work. And furthermore, there's a problem here, right? Because how does the force of gravity work exactly, right? Because Einstein's sitting there and saying that every reference frame is equally valid. In other words, do I use the reference frame of the sun to figure out when gravity acts on the Earth? Or do I use the reference frame of a passing asteroid that's going half the speed of light, right? And then the notion of what now is changes based when you boost your reference frames between one reference frame and another reference frame, it actually changes. And so so this idea that was previously the case, which was gravity was instantaneous, the notion of instantaneous goes away in special relativity, because when you do a boost, you change coordinates between, it's like a rotation in x and y, but you do it between t and x, and so what now means would be like t equal to a constant changes. And so it doesn't make any sense now to say that gravity acts instantaneously. Now today we understand this because it doesn't. It moves at the speed of light also. Gravity waves move at the speed of light. The force of gravity effectively moves at the speed of light. But that understanding is not in special relativity. It's not a theory of gravity. That's what general relativity provides. And Einstein realized that his theory was not compatible with gravity. So let's appreciate that when special relativity first came out, it was on thin ice. It's like, oh, nice. Okay, you explained how the speed of light is the same in all reference frame. That explains the Michelson-Morley experiment. But you're incompatible with, you don't even have a theory of gravity. Like, how does gravity work? Einstein's like, I don't know. Okay, well, I mean, you haven't exactly replaced Newtonian physics then. Newtonian physics can at least get gravity. It's kind of important, right? And so then Einstein contemplated this for years. And so I think it really was, I think it was 10 years between special relativity and general relativity. And I think I heard that like he understood the idea of how to solve it took him maybe around 3 years. And then he spent 7 years trying to figure out how to do the math. Okay, so let me show you his idea. This is the picture idea of Einstein, who, by the way, when I can show you a picture idea of what Einstein was thinking, yeah, that's the level he was thinking. If you're like, I couldn't possibly do that, it's too much mathematics. Einstein did not know that much math. Okay, so when I draw these pictures, realize this is the level of Einstein's thinking. I don't know if it was exactly these pictures, right? But it was qualitative in nature. All right, and then it took him 7 years. He had to go talk to a bunch of mathematicians. Hey guys, I have this idea. How can I make this geometric? How can I make this mathematical? How can I get equations out of this? Okay, so here's the picture. This is the picture that I like. I think, I'm not sure what picture Einstein drew, but I like to think of your bed. Okay? Those are your pillows. That's a bed, right? And now what I want you to do is put a bowling ball on your bed, right? Okay. Now that bowling ball is massive, right? And so it curves the surface of your bed. It puts a dimple in your bed, right? And now take a golf ball and roll the golf ball on your bed. Well, what you're going to notice is if you roll the golf ball, it's going to curve around the bowling ball, right? And why is it going to curve? Well, it's because the surface of the bed is curved. Right? Had the surface of the bed been flat, it just would have gone straight, right? Now, in this analogy, the bowling ball is the Earth. This golf ball here is the moon. And here's the really crazy idea. The surface of the bed, that's space-time. That's x, y, and z and t coordinates, right? All right, so this is sort of the picture of a curved space-time. Now, what Einstein was saying is, look, a massive object curves space-time. Then another point particle, test particle, or massive object like the moon is actually trying to go straight in the space-time, just like an ant trying to go straight on the surface of a potato. But the space-time is curved, and so therefore the moon will seemingly curve around the Earth. But here's the interesting point. Einstein's like, it's not because of some mysterious 1 over distance squared force of attraction. No. Between two objects. No. The Earth is putting a dimple in space-time. The moon is just trying to go straight. And since space-time is curved, it would appear that the moon is curving around the Earth. But in fact, it's just the moon is going as straight as it possibly can on a curved space-time. Does that make sense? Now, in the case of this analogy, if someone were to say, oh, I detect a mysterious force between the bowling ball and the golf ball, you'd say, no, it's not some sort of ghostly force of attraction between the golf ball and the bowling ball. The bowling ball is curving the bed, and of course the golf ball is just trying to go straight. Like imagine an ant walking on the bed, right? They're just trying to go straight, but you're on a curved surface, so they're going to curve too, from our point of view. And so it turns out Newtonian physics is completely wrong in this sense. And in retrospect, it's a little bit embarrassing that you fell for it. It's a little bit embarrassing that you fell for it. I mean, anyone here ever question Newtonian physics and how absurd it is? So the gravity part, you just bought that the whole time. You were just like, okay.
Yeah.
Joke's on you guys. I mean, seriously, what else have you been taught that's completely wrong? Let's just talk about how absurd Newtonian physics is for just a second. And by the way, Newton realized it. The sun is 93 million miles away. The Earth is supposedly being attracted to the sun as if it were on the end of a string. Okay, imagine if I take a weight and I tie a string to it, I could spin it around my head, right? And I would get a roughly circular motion, and the string is pulling the weight towards me, right? And that's how an inward acceleration can cause circular motion, right? Okay, I understand that. Because a string can only pull, it can't push, right? It also can't do anything to the left or to the right, right? So a weight at the end of a string, I spin it, right? That shows how an inward acceleration of force, the string's pulling on the object, causes circular motion. And then Newton said the Earth is going around the sun in roughly circular motion for the same reason. Just like there's a string, and we'll call it the force of gravity, and it's 1 over distance squared. And then his critics at the time said very clearly, okay, Isaac, where's the string? And then Newton was like, I don't know, just the equations work. And then they're like, but this is absurd. You're like, do you believe in ghosts? All right, this was basically the accusation. Where you believe in some sort of ghosts or something, right? There is no string. There's empty space between here and there. Where's the string? And I mean, Newton had to admit, I don't know. It's just that the equations work. In other words, this is a theory based on just because it works. I mean, in other words, it's like, oh, okay, well, we do the math and it works. Okay. It's phenomenological. It's absurd on the face of it. Okay? But then it works, and then we're like, oh, okay. I guess that's the way it is. And the next thing you know, we're like, no one questions it, and it's like, it's amazing how, okay, seriously, we should think of this as human beings, how we just accept things if it seems to work a little bit. It has a little success, right? And then we're like, okay, it must be true. Right? Explains 3 data points or something, right? I mean, isn't that a general human characteristic? And here's the thing about it, that human characteristic works and it gets us by. But the fun of it all is when we realize it's really more fun when we realize how little we know than to pretend like what we really know. Like, you can't go through, I get it, you can't go through life questioning everything, right? Because then you would you'd be indecisive. You'd be like, should I leave the room? Like, what? Well, do I know anything? And then you start to realize, I don't think, do I know anything, right? And at some point you have to be like, okay, look, it's a practical matter here, right? And so as a practical matter, we make various assumptions, and we're like, you know what, Newtonian physics works, I'm going to go with it. You know, it's the best prediction I've got. It's worked for me so far. But as we learn special and general relativity here, and as you learn it in your life, I hope you approach it in the same way that we now know is the case for Newtonian physics, which is, it's not the last theory, it's just the current theory. Okay, so the reason Newtonian physics we accepted it is because it worked pretty well, right? By the way, it doesn't work for the orbit of Mercury. They've known that since, I think, what was it, 1859? I think it was 1859, some astronomers, Verrier, measured the orbit of Mercury and said, whoa, it's not doing what Newton said it should be doing. So as early as 1859, people realized Newtonian physics was only a good approximation. It was not correct for the orbit of Mercury. Now, why Mercury? Well, Mercury is closest to the sun, right? And so the closer you get to the sun, the bigger the next order term is. So it turns out this 1 over distance squared force law is just a good approximation of general relativity. And so Einstein was aware of the fact that Mercury wasn't doing what it was supposed to be doing, according to Newton. He had special relativity. And then he had this idea here, all right? Maybe matter curves space-time. Right? And then he's like, oh, what would the equations be? And he spent 7 years thinking about it, talking to mathematicians a lot, actually. And then he finally wrote down the right equation. Actually, something close to the right equation, not even the right equation. He solved it. He got a prediction for what gravity would be in his theory. And he said, but what does it do for Mercury? He did the computation, it was actually pretty messy. and it got the orbit of Mercury exactly. And that's the moment Einstein realized, like, he was the bomb. I mean, I don't know. It's like in recent history, like what I mean, that is just remarkable, right? To take him, he just completely upended the establishment, right? It's like, and at that moment, he's the one person on the planet who realizes everyone else is wrong about fundamental laws of physics, right? Only he knows that nope, it doesn't work that way. It works this way, right? And so let's get into those equations a little bit. This is where he had to know differential geometry. Basically, he needed this class. Like Einstein needed to do this was this class, right? And if only he could have had this class. Okay, and then also a class after that. Really needed 2 classes in differential geometry. And fortunately for him, differential geometry was being worked out, right? And there were some, these great geniuses, like I mentioned, Gauss and Riemann, right? Did a great job of getting sort of the foundations of differential geometry established. And then you get this picture here and you say, okay, I want matter to curve space-time. And so you're like, oh, okay, how do I do this? And there was a great mathematician alive at the time. His name was David Hilbert. And he's generally acknowledged as the greatest mathematician of his generation. Some people say he was the last mathematician to know all mathematics. And after that, the math became too vast. No one person could know it all. But there was one person who actually knew it all at one point. And his name was David Hilbert, right? So respect, right? Also, do y'all know, I mean, come on, when I say the word nerd is a compliment, right? So David Hilbert, what a nerd, right? Maybe too much. Like, is that possible? Do you guys agree that there is a limit maybe at some point? You should like be a little more well-rounded. No, you're okay. No, it's not. You cannot be too nerdy. Okay.
There's a limit.
I think there's a balance. You want to have look, I'm a believer in work-life balance. I like to be a human being also, right? And sometimes when it's like, the idea, even back then, to know all of mathematics, like, oh my God, it just seems so intimidating, right? But, on the other hand, I love math, and the more math I know, the more fun it is. It is a joyful thing. I hope you guys really enjoy mathematics. It is super fun just to know what you can know. But then, I think the people who know the most are the people who are most dedicated, and sometimes, I don't really know much about David Hilbert. Did he achieve a work-life balance? I assume not. Okay, but I don't know. Maybe someone wants to. By the way, you have to have a paper due Friday, right? If someone wants to write a biography of David Hilbert, that's totally fine. I mean, it could really be anything you want. Einstein as well. I mean, whatever. That paper is for you guys to enjoy. If there's something that inspires you, this conversation, we're talking about all kinds of different things. Like if some aspect captures your imagination, then just write a paper on anything that you like related to what we're discussing. But all Einstein had to do, though, and if he wanted to save himself 7 years, is he just need to go find David Hilbert and say, David, Professor Hilbert, whatever, right? Actually, what do they say in Germany? It's Herr Professor Dr. Hilbert. They have like 3 titles. It's very formal, right? Herr Professor Dr. Hilbert. I want a theory that where matter curves space-time. How do I do that? Right? And essentially, that's when ultimately Einstein talked to a bunch of mathematicians, and through the grapevine, the knowledge got into his head, right? And so what he learned was that he was a physicist, so he already knew. So how do we say that curvature? So he wanted an equation that says curvature equals matter density. That was his idea, right? So how do we? And I want to solve for some space-time here, where curvature equals matter density. So sort of that's the idea. Now you might say, it doesn't seem quite right? Because see, the Earth is curving the surface of the bed, right? But y'all see how the dimple radiates out? So actually, curvature over here is you still have curvature where there's vacuum, right? So what we're really doing is we're going to say a certain kind of curvature, not all the curvature. It turns out curvature is a rather complicated thing. And so if you ask, what is curvature? How about this? What is curvature? Well, in dimension n, okay, it's an n by n by n by n matrix. Okay, you guys know how a matrix is usually has rows and columns. You might say it's an n by n matrix, right? So in 4 space-time dimensions, curvature is a 4 by 4 by 4 by 4 matrix, okay? 4 rows, 4 columns, 4 hyperrows, and 4 hypercolumns. Okay? In other words, that is, what's that? 256 numbers at each point. Okay? So simple. No, no, 256 numbers at each point is what curvature is on a 4-dimensional space-time. Guess what? It's not quite that bad. Turns out this is called the Riemann curvature tensor, and it has a lot of symmetry, so it turns out a lot of those numbers are 0. It also turns out that it also has a certain symmetries and anti-symmetry, so a lot of those numbers are equal, and so a lot of those numbers are the negative of each other, like an anti-symmetric matrix. So actually, in dimension 4, where you say, what is curvature? I'll let n here be the, n is equal to the dimension of, the total dimension of the space. And this is the number of independent curvature, number of independent curvature quantities, curvatures. All right. We're going to be interested in 2, 3, and 4. And 4, it turns out it's only 20. It's only 20 numbers each point. Oh, okay. Well, hell, I mean, that's, plausible, right? So it's 20 numbers at each point. Okay? And in general, by the way, this is going to be n squared times, I think, what is it, n squared minus 1 over 12, I think is the formula. So you put it in a 4, you get 16 times 15 over 12. 16 times 15 is, 240 divided by 12 is 20, right? When you put a log in 3, you get 72 over 12, which is 6. Oh, that's a lot better. That's a lot better, right? But look what happens magically. When n equals 2, you get 4 times 3, which is 12 over 12, which is 1. This is what we're doing in this class. Hey, aren't you happy we are sticking to 2-dimensional surfaces? Okay? There's only one intrinsic curvature quantity. By the way, these are intrinsic curvature quantities, right? And it's called the Gauss curvature, and we're going to become experts on Gauss curvature today. And I mean, in this course. By the way, if you understand this one thing, Gauss curvature, then it turns out that's really the basis for all the other things. So if you understand these 6 and 20 curvature quantities, it's really like 6 Gauss curvatures and 20 Gauss curvatures. Okay, so it's like, for the first thing to do is to learn what curvature is for a surface, and then you can extrapolate from there. Okay. So Einstein had a lot of work to do. You guys appreciate learning differential geometry. It took him 7 years, okay, to be able to get to where he could propose a theory. And so it turns out he's like, oh, okay, this matter density thing, it turns out this is like a 4x4 matrix. Okay? And so this is called the stress energy tensor. And this is like a physics thing, and let's what he realized is this should be interpreted as this 4x4 matrix where you have energy density here. That's in the top row, top column. And then you have 3 numbers here, right? Let's see here. Let's do it very light, okay? Right, but this one I'll do hard, right? Because there's a difference between space and time, right? And this is momentum density. These 3 quantities. And then it's symmetric, so this is momentum density over here as well. Momentum density. Okay, so it's symmetric. It's the point is this is Tij is equal to Tji. Okay. I mean, this is the symmetry right here, okay? And then, so when you flip this way, right? Okay. And then these terms in here are pressures, pressure density, if you like. Okay, so these are pressure densities. And so in total, it's called the stress energy tensor. And so Einstein needed a 4x4 matrix that's curvature to set equal to. By the way, we don't use the term matrix, we use the term tensor. Okay? So tensor means, you can think of it as a matrix. But the point is, a matrix is like a 2-dimensional tensor, right? It's like rows and columns, that's it, right? Turns out we want to have rows, columns, hypercolumns, and however many There's going to have however many dimensions we want. We'll tell you how many we want. A tensor could be. This is an example of a 4 tensor. By the way, not these numbers 4s. It's the fact that there's 4 entries here, right? There's 4 dimensions, right? It's a 4 tensor. And so what we need here is a 2 tensor. And it turns out the simplest curve. If you say, well, what are the curvature quantities? Well, in dimension 4. So I'll just do in dimension 4 here, right? So you have the Riemann curvature tensor. This is a 4 by 4 by 4 by 4 tensor, right? And there's 20 quantities. But you can take its trace, and you get something called the Ricci curvature. And the Ricci curvature is a 4 by 4 2 tensor. And it turns out this has, because it's symmetric, it has 10 independent quantities. You'll see that 4 by 4 matrix that's symmetric has 10 independent quantities. 4 plus 3 plus 2 plus 1. And by the way, you can take that trace, and then you get the scalar curvature. And this is just a number, right? It's the sum of the diagonals of that matrix. And so you could just call it a single number here. And this is just one quantity. Okay? So you see the pattern. When you take the trace of a tensor, it goes down dimension by 2, right? And it's sort of like adding up the diagonals. You see taking the trace of a matrix before, right? You go from a 2 tensor to a number, right? To a 0 tensor. Right? Okay. And I mean, this is just a function. I can put 1. There's number point. I can also put dash. It's a 0 tensor, right? There are no tensor spots at all. Okay. And so then Einstein looked at this and said, well, wait a second. This is symmetric. This is a 2 tensor. Oh, look, there's exactly 10 independent terms because it's symmetric as well, right? Oh, this is really reminding me of the Ricci curvature that's symmetric, right? And has 10 independent terms. And so he said, oh, I don't know. How about we just set this equal to the Ricci curvature? And so this was Einstein's first guess. So his first guess was that the Ricci curvature is equal to the stress energy tensor T here, which goes by T. And by the way, he put an 8 pi in there. And this 8 pi does not have any particular physical significance. It's essentially irrelevant. Okay, you could have left it out if you wanted to. But what's nice about the 8 pi is that if you set the speed of light equal to 1 and you set the universal gravitational constant g naught equal to 1, then it agrees with this theory. Okay. Now, what is you know what the speed of light is? What is the universal gravitational constant? That's where you say the force of gravity from Newtonian physics, which is wrong, so who cares, right? But is equal to, remember, it's m1, m2 divided by the distance squared, but then you have to multiply by some constant to get the units to work out right. That's the universal gravitational constant that we're going to set to 1. Okay? Yes?
Could that be like in our mattress example? Is that like the springiness of the mattress?
You've asked a question I haven't thought about before. I'm going to have to contemplate that. Let me contemplate it.
Yeah.
Let me contemplate it. Analogies are tricky; they're never quite perfect, right? So let me see if you've improved it somehow. But I just want to point out that this G naught, he could have equally set it to 2. He could have set it to 10. He could have set it to pi. He could have set it to anything he wanted to, right? It's just it's sort of this is something that can't. This is simply making it so that when two particles are really far apart, the force of gravity is on the order of m1, m2 over distance squared times 1, as opposed to m1, m2 over distance squared times 2 or any other number you want. Right? So it's a choice. And if you want to do that, then you got to put 8 pi here. 8 pi is what comes out. And you know what? I think it's a good choice. Why not set g naught equal to 1? It's easy to remember. That was Einstein's first guess. But the fact I'm calling it his first guess, you're like, so you're saying it's wrong. And it is. But it's not, it's mostly right. And it turns out, here's what's amazing is, it's mostly right in the sense that, because the first thing he did was he said, okay, well, what happens when I look for a vacuum solution? Let's just solve Ricci equal to 0. Okay. What do you get? Now, you might say, oh, I know, you get, if Ricci equals 0, it means it's a flat space-time. Therefore, it's special relativity, right? Special relativity is a flat space-time. It certainly has, the special relativity over here has Riemann equal to 0. And so we take its trace, therefore, of course, Ricci equal to 0 and the scalar curvature equal to 0. This is a flat space-time, of course, right? It's the simplest one. I mean, it's kind of analogous to the surface of a table, right? Nothing funny going on. But it turns out, remember, this Ricci curvature is only 10 of the curvature quantities, whereas Riemann curvature is 20 of the Ricci curvature. So you're not actually setting the full Riemann curvature tensor equal to 0, only about half of the terms are set to 0. The other half could be whatever you want. And it turns out there are non-trivial solutions. And if you then say, well, what are these non-trivial solutions? Turns out it's a huge number of non-trivial solutions. This is actually a fascinating subject to find all the Ricci equals 0 spacetimes. In fact, it's quite large, unless you assume spherical symmetry, as Einstein did next. And if you suppose spherical symmetry, then you solve the equation. It turns out you just get a one-parameter family of solutions. And by the way, he only found the solutions to top order as this other guy named Schwarzschild, who went back and perfected Einstein's preliminary calculations. And we got what are called the Schwarzschild solutions. You may recognize the name because these are the Schwarzschild black hole solutions on spacetimes. Turns out they have Ricci equal to 0. And I can write down what the spacetime is. Let's see here. How do I want to do it? Where r equals the square root of x squared plus y squared plus z squared. And let's see here, this is squared. And there you go. That's your black hole space-time solution. And it's not the way people normally write it, by the way. I just think it's easier to teach it this. Oops, I forgot my dt squared here. Now, first thing I want you to do is let m equal 0. Notice you get minus dt squared plus dx squared plus dy squared plus dz squared if m equals 0. And by the way, that's what special relativity is. So in the notation of differential geometries, the metric here we write as minus dt squared plus dx squared plus dy squared plus dz squared. This is how you write the metric of a Minkowski spacetime. You take this, and wherever you see a vt squared, put a minus dt squared. It's just notation, right? Just notation. So this right here is saying put a minus sign in the rule of Pythagoras on the t component. This is saying put a minus sign on the time component, and then but also stretch time by this factor and stretch space by that factor in a certain way, right? And the stretching factor depends on r, your distance from the spatial origin, distance, the x, y, z plane, not counting t, right? And it turns out this is the the metric of a black hole. So think of this as a cylinder here. T is going up, and then this would be like the t equals 0 slice. And this right here is a two-dimensional sphere. Everything is one dimension lower than drawn. I'm trying to draw a four-dimensional spacetime. All right, so this right here is an R3 slice topologically, or R3 minus a ball. R3 minus a ball, I guess. And so I draw it as an R2 slice, right? An R2 plane, but it's actually an R3, right? That's not. It looks like a one-dimensional S1, but it's actually a two-dimensional sphere, right? And that's your black hole, right? If you're flying around your spaceship here, don't go in there. If you do, you won't be able to get out. Okay? And why is that? It's because the light cones over here actually are these normal 45-degree light cones. But as you get closer to the black hole, the light cones become taller and skinnier. And in fact, right here they become degenerate at the black hole. And so there's actually a metric singularity at the black hole here, so we can't take it perfectly literally. But you can start to see that your ability to get away from a black hole, even if you have maximum thrust. You guys ever watched Star Trek movies and stuff like that, and there's a black hole, and like, oh no, we're too close to the black hole, maximum warp, whatever, right? I mean, the point is, when you get close to the black hole, even if you're going maximum warp or whatever, because they can go faster than the speed of light, and that's not right, okay? But anyway, if we let that slide, you know, say you're going 99% of the speed of light, you're only barely going to get away from the black hole. Like, you know, you're just barely, if you're going 99% of the speed of light, you're barely able to get away, right? And in fact, if you get too close, you still won't get away, right? But then eventually, as you get further away, okay, now you can get away very easily, right? So this light cone is changing as you get closer to the black hole. So anyway, Einstein was able to compute. He actually couldn't. It's amazing how simple this metric is. Actually, and Einstein was able to compute. He said for large r equals this. He didn't realize that for small r equaled that as well. It's more complicated. It's a pretty complicated calculation, I suppose, especially for somebody who's not that good at math anyway. Right? So we'll give him his respect. He did a good job. It's always hardest to be first. And he realized, he computed the space-time. Then he said, oh, okay, well, what are the geodesics of this space-time? You know, what about the ant walking around, you know, or the bowling ball, right? You're trying to go straight, ant walking on a potato. And so he computed the geodesics of a spiraling, you know, Mercury going around this black hole. And he found out, oh, my God, it explains the orbit of Mercury perfectly. Okay? So what he actually computed was, now why did he compute Ricci equals 0? Well, guess what? The solar system is mostly vacuum. I hate to break it to you, but the Earth is a speck of dust. Right? Did y'all know that 99.8, or is it 99.8 or 9.9? I think 99.8% of the mass of the solar system is in the sun. Which makes sense, by the way, right? Because, you know, people are wondering, like, you know, why do the planets exist? I mean, why don't they fall into the sun? I mean, once you think when the sun was forming, right, it forms this big fireball, but why is there anything, why didn't everything just fall into the sun? And the answer is, yeah, everything did fall into the sun, 99.8% of it. But just by happenstance, some of it got very lucky and happened to be in the right velocity, position of velocity to form an orbit, right, around the sun. And then gravity formed the planets as a result. And so, you know, the sun used to have a ring of gas and dust around it, which then formed the planets. And so, to a good approximation, the solar system is in fact vacuum, except for the sun, right? And so he wanted to say, okay, let's solve for the space-time outside of the sun. So he didn't realize he solved that there would be a black hole for small r, right? That's what Schwarzschild realized. What he realized is for large r, you get a certain shape, and then he did the computation for Mercury, and it checked out. And so that's what this first equation did for him. But then he started talking to more and more differential geometers, and he learned that there was this special curvature tensor that had a very nice property. And there's this curvature tensor, and it's Ricci curvature minus 1/2 the scalar curvature times the metric. Okay, now turns out this is the metric here, G. This is an example of a metric. And more generally, a metric has the same dimensions as a Ricci curvature. It's a 2 tensor. Okay, so the metric is what tells you what the dot product is everywhere. In fact, this is a metric right here, G equal. Okay, so one way you know it's a metric, if you have a 4x4 matrix, right, I can multiply it by 2 vectors, one on the left, one on the right. You know, the transpose on the left and the regular vector on the right, and you multiply it out. You do the same thing with the metric, right? You're taking dot products of vectors, so the metric is actually a 2 tensor. The Ricci curvature is a 2 tensor, so you have a 2 tensor here, you have a 2 tensor there. Think of them as like 4x4 matrices. So 4x4 matrix there, 4x4 matrix there. The scalar curvature is a number at each point. Number is just the trace of this Ricci curvature. And then, so when you look at this in combination, right, this is curvature, Ricci curvature, and then the scalar curvature, it has a very nice property, right? And the property that is key is that the divergence of the Ricci curvature minus 1/2 the scalar curvature times the metric is equal to 0. And that's a mathematical property similar to the fact, I like to compare it to the divergence of the curl of a vector field is always equal to 0. Y'all remember that? And also the curl of the gradient of a function is always equal to 0. You remember those laws? It's a mathematical identity, much like that. Okay? It's mathematical. Okay, it's nothing to do with physics. Well, it has something to do with physics, but it's mathematical first. Because when Einstein learned that, he's like, oh, whoa, I changed my mind. This is not my theory anymore. My theory is now this curvature tensor equals 8 pi t. And let me tell you why. Because if this has zero divergence, that means the stress energy tensor has zero divergence too, and that can be interpreted as conservation of energy and momentum. Okay, so conservation of energy and momentum is like a real thing. It's been observed. It's measurable, right? It's a phenomenon of the universe. It's like, oh, okay, I get that for free if I set the matter density tensor equal to something which has a conservation property, has zero divergence. Okay, so that's like seems like a plausible idea. Okay. And by the way, it's not even obvious Einstein was the first person to write this equation down. This guy, David Hilbert, was a huge fan of Einstein. You know how I remember I said everyone else was kind of skeptical of Einstein, especially when he came up with this stuff. Are you kidding me? When he came up with this stuff, people are like, shut up. and they both, I mean, there's two types of people. People who are like, oh my God, that's genius, shut up. And then there are other people who are like, who the hell do you think you are? Literally, shut up. Like this is beyond what's reasonable. Okay, you know, I'm supposed to take you seriously. Shut up, right? Yes.
How did he get a metric tensor out of the first equation?
How do you get a metric? What's it say again?
How did he get? So you said he used the first guess to get.
Oh, from here to there, it's a complicated computation. Yeah. It's long and complicated, but it's once you take this course and then a graduate course in differential geometry, then it's a weekend exercise. So you know it's doable. You could totally do it, right? It's straightforward but annoying, right? But it's just totally straightforward. Great question. And so, and by the way, you know, this is so radical, right? Matter curves spacetime, but remember this whole idea though that you know, length equals time experience. Well, curvature equals matter density, right? Curvature, that's geometry, right? And so if you, sort of the point of view is, the mathematical point of view affected Einstein very much. I mean, first he had this rather non-mathematical way of thinking of special relativity. Then his math instructor, Minkowski, said, oh, no, you just put a minus sign on the rule of Pythagoras. And then Einstein's like, oh. And then, you know, it got explained to him, no, you define a four-dimensional manifold, right, with this metric. I'm like, oh, okay, teach me more. And then he started learning about differential geometry, and then the Ricci curvature tensor, he's like, oh, well, maybe curvature equals matter density. And so, of course, he tried just the first thing where you have a curvature tensor equaling a matter density. Boom, explains the orbit of Mercury. Touchdown, right? And then someone says, no, there's this other curvature tensor, and it actually has zero divergence. Oh, okay, let's set that equal to matter density. And now we have conservation of energy and momentum in our theory, just automatically built in, local conservation of energy and momentum point at a given point, which is experimental phenomenon. And then Einstein went back to the math nerds, right? And said, okay, are there any other curvature tensors that have zero divergence, by the way? I should probably know, right? Because actually, he's a little bit afraid of being scooped. You know, this guy, David Hilbert, almost scooped Albert Einstein. Because, like I said, most people were skeptical with it, but this other genius named David Hilbert immediately got it. Game respects game, or game recognizes game, whatever, right? David Hilbert did not question Einstein for 1 second. He was like, wow, that's awesome. How can I help? Right? And there were a few other people who did that as well. Eddington, a British astrophysicist, I think. And so David Hilbert got all into it, started nerding out on it, as he would be inclined to do. And it's somewhere in here, David Hilbert, I actually think it's likely David Hilbert wrote this equation down before Einstein. Right? And then, actually he came up with the action of general relativity, definitely before Einstein. And so they call that the Einstein-Hilbert action, but really it's the Hilbert action. And so general relativity really is best understood from the point of view of the Hilbert action, the Einstein-Hilbert action. And then actually Einstein got offended by David Hilbert. At some point he accused Hilbert of not trying to nostrify his theory, right? That's how good Hilbert was. Einstein was like, back off, my theory, right? And then Hilbert was like, okay, I was just trying to help, sorry. And of course it is Einstein's theory, right? I mean, Hilbert was just like getting on board trying to help out. Anyway, this would be the this is, by the way, this tensor right here is called G. So this is G is equal to 8 pi t. If you hear about the Einstein equation, G is defined to be this tensor here. And then remember I said Einstein was like, guys, are there any other tensors that are conserved that have zero divergence? And then, of course, the answer is quite interesting. The answer is, well, yeah, actually. In fact, they're an infinite number. And so you all should keep that in mind, that it's actually not that special to have zero divergence. In fact, anything that comes from an action, as David Hilbert showed, will have this zero divergence property. And I won't talk about actions today, but it's something to think about for the future. But if you say, how about actions which are of are only two derivatives in the metric? In other words, the simplest types of curvature tensors. There are only two derivatives in the metric. What are the simplest ones? It turns out there's only a one parameter family. You could say you take that G, and then you can add in any constant multiple of the metric. Remember, this little g here is the metric. You can add in this Einstein curvature tensor plus 5 times the metric, for example. This also has zero divergence. So it makes sense to set this to equal 8 pi t. And that theory is just as good as the second one. And so this right here is called the cosmological constant. And so Einstein next said, okay, how about, he actually proposed it, cosmological constant. So he proposed 3 versions of general relativity. The first one, which he abandoned, and there's no reason to go back because this Ritchie is not conserved. So it doesn't have zero divergence. The second one, G equal 8 pi t, which is often cited as general relativity. And the third one, which actually describes the universe the best, as we understand today, which is to add this cosmological term in there. When Einstein introduced it in his day, he recognized it was a natural thing to do. He was trying to explain a static universe. But this was before the American astronomer Hubble in the late 1920s realized that the universe, in fact, is expanding. And in fact, it's not static. But Einstein didn't know that, and so he introduced this constant to try to get a static universe that had always been and always would be. And it turns out it doesn't work. It turns out you can get a static universe, but it's unstable. So you perturb it a little bit. It's like a pencil on edge, right? It's going to fall, right? So you can't get this sort of universe that always existed and will always exist. And so he realized, so he referred to the cosmological constant as the biggest blunder of his career. And then Einstein grew old and died. And then physics and math continued to advance. And at some point, people got really good telescopes and other astronomical equipment. And then people started measuring the expansion of the universe. And then around 2000, some astronomers realized that the expansion of the universe was accelerating. And then everyone realized, oh, we need a cosmological constant. And so 50 years after Einstein died, it's become standard to put a cosmological constant in the Einstein equation. And by the way, the people who observed the data that said they must have a cosmological constant to explain the universe, they got the 2010 Nobel Prize in Physics. So what I think is funny is that someone actually got a Nobel Prize in physics for what Einstein called his greatest blunder, right? So it wasn't a blunder. It was actually very insightful. This is a very, very natural thing. And you might say, well, what is the cosmological constant? Well, it turns out it's very, very close to 0. So if you want to match up with the universe, it turns out you want the cosmological constant to be very, very close to 0. Topics for your paper, since you're trying to decide, by the way, is that the actual space-time metric of the universe, it's not this. The next best approximation is to put a stretching factor, A of t squared, on the x, y, and z terms into some approximation. This is called the Friedmann, Lemaitre, Robertson, Walker space-time metrics, FLRW space-times. And turns out that, what is that A of t? The A of t looks something like this. And A of t in particular used to be 0. And when this A of t was 0, we called that the Big Bang. So the Big Bang happened at t equal to 0. The size of the universe was 0. It exploded into existence in terms of observations. And there are these various epochs. It was originally dominated by electromagnetic radiation, then regular matter and dark matter, and now dark energy dominates the universe. The fact that it's curving up here is unexpected. That's the accelerating expansion of the universe. 2010 Nobel Prize in Physics. I'm not sure if anyone got a Nobel Prize for the Big Bang, but they should have. Maybe they didn't, right? But Hubble observed that the universe was expanding, and then this Friedman, Lemaitre, Robertson, Walker, before them independently at different times, figured out that the Einstein equation here predicts that there's either a Big Bang in the past or a big crunch in the future. And then that combined with Hubble's observation that the universe is expanding suggests that there was a Big Bang in the past, and then better measurements and so forth, they estimate around 13.8 billion years ago. And the universe was hotter than the inside of the sun. I mean, in some sense, infinitely hot when the Big Bang happened. And in fact, the universe was very much like the inside of the sun for like the first 50,000 years. Like you couldn't see anywhere, right? Just like if you were the inside of the sun. And it became transparent, but still extremely hot. And as it expanded, the electromagnetic radiation with the wavelength got stretched out. And today, light, we don't even think of light as having mass, right? Or energy. And it has a little bit of energy. It has gravity, actually. But it's so small, right? But it used to be most of the gravity in the universe was, in fact, electromagnetic radiation. That was for the first 50,000 years after the Big Bang. And then regular matter and dark matter dominated for the next 10 billion years. And for the last few billion years, dark energy has dominated, meaning that this term here is dominating sort of the curvature of the universe. So black holes, Big Bang, dark energy, dark matter, accelerating expansion of the universe. If you want to know more, write a paper on it, turn it in Friday. Short, just fun. Take a topic that inspires you, learn a little bit more about it, write a 3-page note on it. Everybody gets an A. Okay? Does that sound good? Yes.
How strict should we cite in this?
I'll put a bibliography, just like one or two, whatever citation. By the way, it's usually better to have more than just one citation. I would allow it, I guess, if you really want to, but put 1 or 2 or 3 citations in there just to round it out. All right. See you guys next week. Enjoy.